In this video, we'll create solids in 3 dimensions by rotating a region around an axis. Then we'll use calculus to find the volumes of those regions. Let's begin with the graph of a function that is f of x equals the quantity 1 minus x times the quantity x minus 6. Let's look at the region cut off by this curve and the x-axis. Now let's shade in that region. Previously, we've been able to compute the area of this region, and we've been able to build a solid with this region as its base. But what if we rotate this region around the x-axis? What would that solid look like? It would look something like this. How would we find the volume of this solid? We could take a small, thin slice of this region perpendicular to the x-axis, and when we rotate that slice around the x-axis, we would get a disk. As we vary the location of that slice, we get a larger disk or a smaller disk. But in each case, we can find the volume of this disk rather easily. Let's do that. For reference, here's a graph of our region in the xy plane. Here is a representative slice. In order to find the volume of the disk, we need to find the radius of the disk, which will be this height here, extending from where y equals 0 up to where y equals f of x. Notice that we won't get an actual disk. It will be a disk with a bit shaved off the edge. But this should be close enough as we let delta x, the thickness of our slice, get smaller and smaller. For reference, here's a sketch of our region, and here's a sketch of a representative slice. We can also sketch what that slice looks like as we rotate it around the x-axis. We get this disk. In order to find the volume of this disk, we need to know its radius and its thickness, which we'll call delta x. The volume of this x slice would then be pi times the radius squared times delta x. The radius in this case is the height of the function, which would be the quantity 1 minus x times the quantity x minus 6. We can then add up all of these slices for various values of x, and this will approximate the volume of the entire object. This sum is a Riemann sum, and it will converge to an integral of pi times this radius function squared, and then we get a dx in place of the delta x. And in order to get every possible slice of this region, we need to let x go from 1 to 6. So the limits of our integral will be from 1 to 6. Because this definite integral is the integral of a polynomial, we're able to work this out exactly, although the process may be a bit tedious. Using technology, we can see that the answer will be 625 pi over 6, or approximately 327.25 cubic units. So the volume of this solid will be a little more than 327 cubic units. What if we wanted to take this same region and rotate it around a line other than the x-axis, say the line where y equals -2? In our sketch, our axis of rotation would be down here. If we rotate the region about this new line, we will get a different three-dimensional object. What will that look like? It will look like this. Zoom out so we can see the whole thing. So it looks like something like our previous object, but with a hole in the middle. What will the slices look like as they get rotated around this axis? Here's the slice, and here's what it looks like when we rotate it around that line. We get what we might call a ring, or in technical mathematical terms, an annulus, or it might look like a washer, an object that you would use with a nut and a bolt. Essentially, it's a disk with a disk cut out of the middle. If we take our blue slice and rotate it around this red line, we will now get one of these washers. What will the volume of this washer be? Its thickness will again be delta x, and the cross-sectional area will be the area of the large disk minus the area of the small disk. So the volume of our x slice in this case will be pi times the big radius squared minus pi times the small radius squared, all times the thickness of the slice, delta x. In our case, the big radius extends from the line y equals -2 all the way up to the top of the graph. This distance will be the function height minus -2, or +2. What will the little radius be? In this case, the little radius will always be 0 minus -2. Adding up all of these volume slices gives us an approximation of the volume of the object. I'll factor out a pi. So we have the quantity 1 minus x times the quantity x minus 6 minus -2 would be +2 squared, minus, we factored out the pi, 0 minus -2 is 2 squared, delta x. And this is a Riemann sum that then converges to a definite integral, pi times the quantity. First we have this big radius squared minus the small radius squared. The delta x becomes a dx. And again, we integrate from 1 to 6 because we need every possible slice for this region. We can work out this integral by hand. It's merely a polynomial, although a rather complicated one. Or we can use technology to find that the exact answer is 375 pi over 2, which is approximately 589.05. The volume of this solid is approximately 589, which is substantially bigger than the volume of our previous solid, which was about 327. As with our previous volumes, we don't actually need to know what this object looks like to find its volume. All we need is a sketch of the region, a sketch of the axis of rotation, and a sketch of our representative slice. Rotating this slice about an axis perpendicular to the slice will give us either a washer or, if the axis of rotation is adjacent to the bottom of the slice, a disk. If we were to rotate this slice about some other axis, and our rotated slices were not disks or washers, we would need another method to find the volume of the object. More on that later.